The first thing we're asked to evaluate in this problem is the magnetic flux through the loop due to the current I in the wire. That magnetic flux is the integral of B dot dA over the loop area. We know from the right-hand rule that the magnetic field from the current I will circulate in this direction, so that inside the loop area the magnetic field is directed into the screen. And we know from Ampere's law that the magnitude of that magnetic field is mu naught times the current I over 2 pi r, where r is the distance from the wire. The loop has an area A that we can assign a direction to. It's perpendicular to the plane of the loop, and I'll show it directed into the screen in the same direction as the magnetic field, so that a differential area, dA, will look like this and have a magnitude of L times dr. If we return to our expression for the magnetic flux, we see that B dot dA simplifies to B times dA because B is parallel to the differential area vector, and we can substitute our expression for B and for dA. When we integrate from r equals A to r equals B, we obtain the expression we were asked to find. The magnetic flux is mu naught IL over 2 pi times the natural log of B over A. Part B asks us to do two things. First, we're asked to find the direction of the induced current, either clockwise or counterclockwise, and then we're asked to find the induced EMF around the loop. We can use Lenz's law to find the direction of the induced current. As the current I in the wire increases, the magnetic field B increases in magnitude and the magnetic flux increases. Lenz's law tells us that the induced magnetic field will counter that change in flux, so the induced magnetic field, which I'll draw in red, must be directed out of the screen. Then we use the right-hand rule to see this magnetic field must be due to a current in this direction, which is counterclockwise around the loop. The second thing we're asked to find in Part B is the induced EMF around the loop. We find that using Faraday's law. The induced EMF is minus the time derivative of the magnetic flux. The only quantity in the magnetic flux expression above that varies with time is the current I. So when we take that time derivative, we have all the constants times di dt. Part C asks us to evaluate this EMF given a set of numbers. We can substitute those and calculate. Finding the induced EMF is negative 5.06 times 10 to the minus 7 volts.